I'm Katherine Tung from Menlo Park, California. My research is about partially ordered sets, also called posets. Posets can help model everyday decision making. When we're presented with several options, we can often order them from most preferred to least preferred, but sometimes we find a couple of options that we can't choose between. Say you're driving and you're looking for the nearest gas station. Perhaps the two closest stations are the same distance away, and it's not clear which is preferable. Options that we can't decide between can be captured mathematically using posets. For my project, I studied a class of posets called 132 avoiding intervals. These structures are relevant to multiple areas of math and computer science, including algebraic combinatorics, algebraic geometry, and graph searching algorithms. You may be wondering, what are 132 avoiding intervals? Before answering this question, we'll need to define 132 avoiding permutations. A permutation avoids the pattern 132 if there are no three values such that the first is smallest, the second is largest, and the third is second largest. A 132 avoiding interval is an interval from the identity permutation to a permutation that avoids 132. Examples include e to 312. For a more complicated example, consider e to 4123. Note also that the symmetric group itself is a 132 avoiding interval, specifically the interval from e to the permutation n, n-1, n-2, all the way down to 1. Here's an example. This is S3. You may be wondering, why study 132 avoiding intervals? I'll offer two perspectives. First, 132 avoiding intervals are an interesting generalization of prior research on the spurnarity of Coxeter group posets and subposets. These structures have been an active area of research over the last few decades. In a 1980 paper, Richard Stanley proved that all maximal parabolic quotients of Sn in the weak order are Sperner, and he resolved an open problem of Erdos and Moser. In a 2020 paper, Christian Gates and Ibo Gao proved that all minimal parabolic quotients of Sn, in other words, all of Sn, are Sperner and resolved an open problem of Richard Stanley. The 132 avoiding intervals I define include all parabolic quotients, the maximal ones, the minimal ones, and the ones in between, as well as infinitely many other posets. So proving the 132 avoiding intervals are Sperner serves to unite and extend these two results due to Stanley and Gates and Gao. As for the second perspective, the concept of 132 avoidance is important in the study of Schubert polynomials in algebraic geometry. As it turns out, if sigma is a 132 avoiding permutation, then the principal specialization of the Schubert polynomial for sigma is 1. My project offers a new proof of this result. Essentially, we construct SL2 representations on 132 avoiding intervals, and then use these representations to derive an analog of McDonald's reduced word formula. Our formula makes it apparent that when sigma is a 132 avoiding permutation, the principal specialization of the Schubert polynomial for sigma is 1. So the main idea here is that the spurnarity of 132 avoiding intervals gives us a useful new formula for evaluating Schubert polynomials. Now you may be wondering, are 132 avoiding intervals relevant outside of mathematics? They are relevant to graph searches in computer science. There is a bijection between 132 avoiding permutations and full binary trees. Also, for a given 132 avoiding permutation, there is a bijection between elements of the 132 avoiding interval and linear extensions of the tree. A linear extension is the labeling of the nodes so that every parent node has a smaller label than its children. Therefore, linear extensions can be interpreted as search orders on the trees. We have shown that 132 avoiding intervals have the Sperner property, so our result may help bound the number of incomparable search orders of the trees, and thus optimize search algorithms like depth first search on trees. Search algorithms like DFS have a variety of applications, like finding search results and getting driving directions. I hope my work will eventually speed up these processes, which are essential to many of our lives. Thank you.